Hello, this is Peter from Educommondo and a warm welcome to our STEAM project number 19, in which we will build a rotating clock. These lessons are for the absolute beginning STEAM teacher. No prior knowledge of programming or electronics is required. We call this level the Explorer level. The goal of today is to control the hand of a clock by using a new type of motor, the stepper motor. We will use a special library for this motor called stepper.h. We will also introduce a new motor driver, the ULN 2003A, and most importantly, we will have our class work as a team. Let's take a closer look at the stepper motor. This motor resembles a lot the servo motor. It also consists of three main parts. There is the small electric motor, a gearbox, and an output spindle. Because it moves the central output in small increments, this motor is used in printers, 3D printers, robotic arms, and other applications where high precision is required. There are many models on the market, from large ones to the smaller one that we are using, the 28BYJ48. Let's have a look at the basic working principle. The motor is connected to the Arduino by means of 5 wires, 1 power line and 4 control wires. Each of the control wires is connected to one of the 4 coils that are activated in a specific sequence to make the motor turn in precise steps. Most stepper motors advance in steps of 32 or 64 steps. These steps are transferred to a gearbox, where the primary number of steps of the motor are multiplied through a set of cogwheels. That way, even a simple stepper motor can achieve 2048 steps for one rotation. So dividing 360 degrees by 2048 steps gives us a step angle of 0.176 degrees. The other component that we introduce today is the motor controller. Depending on the starter kit, this controller can have different formats. A popular one is this with a selector between 5V and 12V and some large LEDs indicating which coil is activated. In the Key Studio starter kit, there is another smaller version. Because the chipsets on these controllers are so small, it is often very difficult to read the type, and a magnifier glass is no luxury. Here you can see the type using a digital microscope. Now that your students are acquainted with the main components, let's hand them out. We start with the microcontroller and the breadboard. This is our stepper motor. We have the motor controller. We will also use a DuPont cable with male and female endings. We need a black jumper cable to connect the breadboard with a microcontroller and have a common ground. Next is our external power supply. Because this stepper motor draws quite some current, it is best to use an external power supply. We need a 9V battery with a power plug, and of course the cardboard figure of the clock and the hand. It might also be useful to have some sticky stuff like double-sided tape or buds to fix the motor on a plate. We start by connecting the DuPont wire to the motor controller. Because we want to use as much as possible the same colors as the ones used on the stepper motor, we take the blue, the purple, the yellow, and the orange wire. The brown and the red wire will be used as the power cable and the ground. On the other side of the controller, you can see the indications VCC, ground, and then in 1, in 2, in 3, and in 4. We look at the white connector plug on the stepper and apply the same color sequence. As you can see, blue and red are on the outsides, and then we have the purple, yellow, and orange one. The white connector can now be clicked in the socket. Make sure your students are putting it in the right way and do not force it. Next, we add the external power supply to the breadboard, making sure that the plus and minus outputs are aligned with the plus and minus rails. We add our 9-volt battery, but don't yet switch on the power supply. At this stage, we connect the ground of the microcontroller with the ground of the power supply so that we have a common ground. Now we connect the male side of the DuPont cable to the digital pins of the microcontroller. We take pins 2, 3, 4 and 5. In the end, you can take any digital pin that you like. However, the sequence is important. These pins will control the order of activating the coils, and that activation has to be done in a specific order that is different from model to model. So you might need to do some experimenting before you get the sequence right. In our case, the order will be blue to pin number 2, yellow to pin number 3, orange to pin 4, and purple to pin 5. And lastly, we connect the red and the brown wire to the positive and negative rail of the breadboard. That's it for the hardware. Just like the servo motor, we will work with a library. This library is called stepper.h. This library comes with the Arduino IDE, but is probably not yet installed. To do that, we go to the Library Manager, look for Stepper, and install the library. And as you can see, this goes very quickly. We start by putting the name and the variables at the top of our sketch. So lesson 19, clock rotation, variables and declarations. And the first thing we do is we use #include the library stepper.h. Next, we define a variable that sets the number of steps per rotation. For our model, this will be 2048. So an integer, and we call this integer steps PR, equals 2048. PR stands for per rotation. We also need to set the speed of the motor. by creating a variable called step speed. As always, you can use any name, but use something meaningful, not just any random abbreviation. And it's always a good practice to define a global delay variable. So int dt equals 500. As with most libraries, we need to create an object out of that library. And we call this object myStep. So stepper, myStep, and this object takes a couple of arguments. The first one is the number of steps per rotation, and then the sequence of the pins. As we said before, this might require some experimenting, as the wiring can be different between stepper models. For our model, the sequence of the pins is 5, 4, 3, and 2. Let's go to the setup function. Just in case we want to check something on the serial monitor, we started with serial.begin and the baud rate of 9600. To set up the stepper itself, we use the function setSpeed, and the argument is the variable step speed. So myStep.setSpeed, and in between brackets step speed. Now it's time to go to the function loop. In the loop function, we are going to use the command step to make the stepper go forward with the number of steps as defined in the variable steps_pr. Once a full rotation is done, we can make the clock go backwards by using a negative rotation. So myStep.step, and in between rounded brackets steps_pr, followed by the delay dt. And as we said, once a rotation is done as defined by the variable steps_pr, we can make the clock go backwards by using a negative rotation. myStep.step, and in between brackets minus steps_pr, followed by a short delay. Let's upload the program and see what our clock is doing. Once everything is working, you can ask your class to experiment with, for instance, using 4096 as rotation steps, or using a higher number than 10 as the stepper speed. If it doesn't work, no panic. Let them do some logical fault finding, just as we did in the past. Were there any error messages in the Arduino IDE? Aren't there any loose wires or connections on the breadboard? Have you checked all components? Is there a proper USB connection between the computer and the microcontroller? Let's revisit the goals of today's lesson. First of all, we controlled the hand of a clock by using a new type of motor, the stepper motor. We learned how to use a special library for the stepper motor, stepper.h. Our class has gained experience in attaching the motor driver, the ULN 2003A, to the microcontroller. And we had our class work as a team, which in turn triggered their critical thinking. I hope that you and your class enjoyed experimenting with this project. Time to wrap up with some assignment ideas. Since we've been talking about clocks, here are some assignment ideas concerning clocks. Can you find 5 examples of types of clocks? What is the clock speed of a processor? And can you find the clock speed of the Arduino microcontroller? Why is time not measured in a decimal system? What are global time zones? A nice exercise is to find the time in cities that are 1,000, 2,000, 5,000 or even 7,000 kilometers away from where you live. And around the world there are different ways of indicating years and eras. Can you name a few? As always, these are just some suggestions. As a teacher, you know your class best and you are ideally placed to come up with your own assignments. This concludes our Project 19, the clock rotation. It also concludes our series on electronic motors, in which we covered DC motors, servo motors, and stepper motors. In our next lesson, number 20, we are going to look into sensors. We will start with the DHT11 sensor, which combines temperature and humidity reading. In this lesson, we will use all of the skills that we have seen in the previous lessons to make a portable weather station. Take care and bye-bye for now.